a new experimental setup for collecting nRF2.4 and LoRa devices signature for machine learning-based device authentication. Longest name ever. My name is Zheng.
And I'm William Hemminger.
And we are currently a senior undergraduate student at Penn State Barron. And this work was supervised by the faculty advisor, Dr. Abdallah. And by the title, you may notice that we are interested in device authentication with device signature from the wireless signal. Why would we care about identifying device based on its own wireless signal? Well, as we all know, there are growing dependencies on wireless technologies nowadays, and more sensors and wireless devices are needed in the revolutions of Internet of Things and Industry 4.0. For example, there will be also more and more local network of devices that require device fingerprinting to prevent possible malicious attack. And of course, device fingerprinting will need unique features for different devices, and which we can find across the wireless protocol stack. But ideally, what we want is some features that is device specific and non-forgeable. So what kind of features we can find? For example, we know there are MAC and IP addresses in the MAC and network layer. They are used to track the device in the network, and they are easy to spoof and manipulate with the help of software. So this is not something what we want. So if we look deeper into the physical layer, we have features such as the received signal strengths and IQ samples. But remember, we want something that is device specific and non-forgeable. So we may want features that utilizes or related to the manufacturing imperfections. So what we eventually chose or look at is the IQ sample. The imperfect manufacturing process leaves non-forgeable features in the IQ samples. No perfectly identical ICs could be made even with modern manufacturing technology. The question is, could we classify them? And if you look at the figure at the lower right here for a typical transmitter chain, you can see there are various RF impairment source exist in the different stages of the chain. There is harmonic distortions in the digital to analog converter. There is nonlinear distortion in the power amplifier that comes with its nonlinear behavior. There is the most important IQ imbalance that because of the phase or amplitude error in the quadrature signal it generates. So as we all know, such imperfection exists in our devices. We should be able to collect and classify this information using a similar approach as facial or fingerprint identification with the help of neural network or another possible machine learning techniques. So to collect the desired IQ samples, software-defined radio naturally becomes our very first option because of its extreme level of configurability, allowing us to collect data for different kinds of RF devices for future processing. So let's look at what we did in this summer. What we did is that we created a setup that uses software-defined radio to collect IQ samples for the chosen RF devices. And we chose two types of devices in the markets. The first one is this Heltec Wi-Fi LoRa 32. And the second one is nRF2.4 L0 and Plus. You can see what they look like in the figures here. And we chose the ADAS USRP B200 to collect our data set.
Okay, so why did we choose nRF and LoRa? Well, first of all, both of them are very popular in Internet of Things applications. For example, nRF is extremely popular in the Arduino robotics community, and it uses Gaussian frequency shift keying, which is the same modulation scheme that is used in your Bluetooth devices like your wireless headphones, keyboards, speakers, etc. Whereas with LoRa, on the other hand, it's most commonly seen in large-scale monitoring applications, like relaying soil moisture content data to a farm. or tracking the strain on a distributed power grid, or making buildings smarter to improve energy efficiency. And LoRa is ideal for these kinds of situations because of its capacity for long-range transmission. And this is because the LoRa modulation is a subset of chirp spread spectrum modulation, where the frequency varies linearly over time. And this makes it very easy to decode even over long distances. And actually, I was just looking up earlier, I think the new distance record for LoRa is, with a 25 milliwatt antenna, is 832 kilometers, which is pretty significant. LoRa is also, of course, extremely popular with LoRaWAN network applications, where you'll have LoRa transmitters like sensors sending data to a gateway, which then interfaces with the LoRaWAN server. And that server can then either send information into a database or to some custom program for later use. We see here that the nRF devices operate in the 2.4 gigahertz to 2.525 gigahertz range, whereas with the LoRa's, they're in the megahertz range, most commonly seen in these 4 distinct bands. And by using both of these devices, we are hoping to be able to mimic or represent a fair amount of Internet of Things communication scenarios. So regarding the configurations for our devices, we tried to provide optimal communications conditions using the provided device settings. So for the frequencies, we chose frequencies that are recommended for the respective device's use. We also set the transmission power to the maximum possible level for that device. So for the LoRa devices, that value was 20 dBm, whereas for the nRFs, that was 0 dBm. And to ensure consistency, we made sure that the preamble should be static, because we want to use the preamble for device fingerprinting. So we want to analyze that specific segment. Anything else to mention here? Anything else to mention here? Is that it? We good here? Okay. All right. That's good. Moving on with our actual experimental setup, you can see that we have 2 Raspberry Pi computers. They're interfacing with the nRF devices using C and C++ programs. We also have our EDIS USRP B200 software-defined radio that is using GNU Radio, and that's interfaced with an Ubuntu 18.04 laptop. And the reason why we are using a receiver and not just the B200 on its own is so that we can quickly verify and validate each data collection trial. Because the nRF and LoRa devices are on fairly common frequencies, it's possible that our data set could be corrupted by interference from some unknown source, and that will easily register immediately on our receiver, and so we'll know not to include that specific trial in our data set. And because we want to collect from a huge pool of these devices, LoRa and nRF, we want to make sure only to change the component of interest in each trial. So for example, we won't change the antenna we're using with every trial unless specific factors or effects of that antenna are necessary for the study. So for instance, we would only change the transmitting chip and keep the same antenna between each trial. So with our physical setup, on the left we have the nRF modules, and on the right we have the LoRa modules. We have the Raspberry Pis fired up, we have the laptop fired up, and you can see that the B200 software-defined radio is aligned with the receiver. This is to minimize discrepancies between the traffic received from the B200 and on the receiver. So if the receiver says, hey, we've got a problem with this data, most likely the B200 does as well, or if things look fine on the receiver, the B200 most likely is fine as well. And we are approaching the end of our presentation, but moving forward, this is still ongoing work, so we hope to publish data sets using different variations of transmission parameters, one of which being the transmission power, bandwidth, etc. And we also hope to begin incorporating machine learning classification into our device signatures, so actually being able to classify what each device fingerprint is, and also to just explore different applications for device signature and device fingerprinting in Internet of Things. So it's really interesting, especially as Zeng mentioned before with security, the types of ways this can be implemented and the different applications that it's used for. And especially now that we're more interconnected than ever and online and over wireless networks, our credentials are really very important. So our last slide, we want to thank you for having us here. Again, we're undergraduate students, so this is a really impressive conference to attend, and it's been really wonderful seeing all of your presentations as well. If you want to see our work, we have our GitHub link down below. Also, our contact information isn't listed here, unfortunately, but you can contact us. You can reach out to us personally. While we're here, we'll be here until Thursday. And if you want to see our poster, it is in, again, the exposition hall where the food is for lunch. So we should all know where that is. And I believe that is all that we have. So thank you again. Thank you very much.